Hello everyone and welcome to the problem solving session for the course Basic Electronics of NPTEL. Uh, the number is NOC 23 EE62. This is the fourth week of the problem solving session, today being February 25th, 2023. And my name is Amit Bansal. I'm a PhD scholar at IISc Bangalore. So as I was saying that we have been the three previous sessions. In the first one we had talked about the Thevenin equivalent of a circuit and Norton equivalent, and then we also saw that how we switched between the Thevenin and Norton equivalents as per our requirement. And then we saw a few problems on the nodal analysis and the superposition theorem, and finally we saw the phasors. So if you recall, phasors are nothing but the sinusoidal steady state of a current or voltage. In second session we saw some circuits using RC transients, and we also saw a few problems on RL transients. And then more importantly we saw that how the switching impact on the transients, right? So when we change the position of the switch from one to another, how are the transients impacted? Finally, in session 3, that's last week, we saw how to solve some diode based circuits. So diode we typically denote it as conducting only in one direction, and thus it gave results to some peculiar circuit properties, right? um, so building on that, today we first discuss about a few the another diode based circuit. It's a fairly common circuit known as the half wave rectifier. So as the name suggests, so what we do is that on the input side we input a sinusoidal input. Like you can see, this is an AC waveform with V oscillating between Vmax and minus Vmax at a certain frequency. And this input waveform is now fed to this circuit, which has a diode and a resistor R and a capacitor C, and output is we measure the output across the resistor or the capacitance. You may see it either way. Now let's just first forget about the capacitance for a minute, and let's just see how will the output look like. So the circuit will only have D and R, that is, and we are assuming ideal diode here. So that means in the positive half cycle, right, this diode will be forward bias, because this so whatever the input will be providing at the Vs will simply reflect at the output. So in the positive half cycle you will see this dashed line. However, in the negative half cycle, that is when the input is this bottom half, this diode will be reverse biased, and hence no current will flow. So whatever voltage so no current will flow. So if you say V equal to IR, so if I equal to 0, the voltage measured over here V out will naturally be 0, which is this straight line that you see here. Again, if the positive half cycle comes, this diode will start conducting, and the output will simply follow the input, because this diode will behave like a short circuit. And again you see this the dotted line that you are seeing. So this will repeat, and that's why it's called a half wave rectifier. So what we are doing is that in half of the time the circuit is conducting, you see this dotted line, while the other above it's not. That's the meaning of a half wave rectifier. And we can improve this by adding something called a smoothing capacitor or a filtering capacitor. So you see, and this is the output waveform, solid black, that you are seeing. So let's just again see, when in the positive half cycle this diode will be conducting. So what's happening, this diode will be providing the current to this resistor. Also some current will flowing through this capacitor, and this capacitor will get charged, right? What happens in the negative half cycle, this diode will be turned off, but this capacitor will now since this is charged, so there'll be a current flowing in this RC circuit, and thus this will be decaying slowly, and hence which is denoted by this straight line. Now we'll choose the time constant of this circuit. If you remember, tau equal to RC. This tau we choose in such a way, the values of R and C, such that tau is greater than T. What is T? T is nothing but the time period. So you see, this is the time period T. So if we choose it in such a manner, and this discharges very slowly, right? This is not hit 0. And so in the positive half cycle the capacitor gets charged, in negative half cycle it gets discharged, and hence you get this kind of a waveform, right? This kind, and this is also called a ripple type of a waveform. And we'll see in the following, when we discuss problems, we'll discuss in much more detail. So now let's just quickly jump to the problem. So the first problem for today says, consider a half wave rectifier with Vm equal to 25 volts, frequency is 50 Hertz, and a filter capacitance. We have seen the filter capacitance smoothing capacitance, a filter capacitance of 500 microfarad. If the ripple voltage is to be limited to 2 volts, now we'll just define what do we mean by ripple voltage, but is a lower limit on the load resistance. Okay, so we need to find the what is the value of the RL, the load resistance. Okay, and we are considering diode to be ideal, that is V on should be 0. And these are the 4 options. We'll see how to solve this problem. So this is the circuit, I just replicated it, so all the relevant details are here. This is the input waveform in red, and you can see the time period is t. So how do you calculate the time period t? Simply it's 1 upon f. Frequency is given 50 hertz, so time period will come out to be 20 milliseconds. So this time period is from this to this is 20 milliseconds. Okay, now as we saw just in a couple of slides before, that the output waveform will look something like this. So capacitor will get diode will conduct and it will charge the capacitor. So you can see here in this again it will discharge during this flat period, and then again when the positive waveform comes, and when the diode becomes forward biased at this junction, it will again start conducting, and thus the output waveform will simply mimic the input waveform, which is this sinusoidal over here. And at this junction, diode becomes reverse bias at the peak, and then what you will see is nothing but excuse me. And after this, what we'll see is that the diode now gets start to discharge. At this junction, diode becomes reverse bias, and hence only RC circuit will work, and this capacitor will discharge, and we will see such kind of a straight line in the output waveform, right? So this is what we are denoting it as here. So this is a discharge. This straight line is a discharge, while the sinusoidal output waveform is when the capacitor is charging, and this time I am denoting it as T0, where let's say where the discharge and charge cycles, where the charging cycle takes over from the discharge cycle, right? So as a step one, so we'll now notice when the discharge, when it's discharging, when that is the capacitor is off, when the diode is off, capacitor discharging, that is this time period via the resistor R, and we can simply write the simplistic expression V naught equal to Vm e to the power minus t by tau. V naught is the output voltage, Vm is the maximum voltage which is given in the problem. And we are assuming that, so just for the sake of simplicity, let's assume that this is the time t equal to 0. Okay, this is just for simplicity. So that's why it looks e to the power minus t by tau. Now, if t is less than tau, that is time period is less than tau, we can simply write I should say it's rather like this. So the time period t, right, is less than tau. What's going to happen? We can approximate it by a linear expression. How do we do that? Because you know the exponents of x can be expanded like this: 1 plus x over factorial 1 plus x square over 2 factorial. And by using this, you can just simply drop the higher order terms, and thus this expression, exponential expression, will simply boil down to the linear expression, and hence you see this straight line. But note, this is the assumption. All right. So now we have the expression for output waveform. Now what we'll do, just after one discharge cycle, that is at this junction, right, but and we're noting as t equal to t0, the two voltages should be equal, right? So what's the voltage here? Vm, this is the peak voltage, minus Vr. So this is what we define as the ripple voltage, this peak voltage minus this. So this is what we define as the ripple voltage. That is the extent to which the voltage has dropped, the output voltage has dropped while the capacitor was discharging. So we can say that Vm minus Vr, that is the voltage over here, right? This should be equal to, according to this formula, right? That if I put small t equal to capital T, and I'm just ignoring this very small time, okay, just for the sake of simplicity, we can assume that small t equal to capital T. That is, this is discharging for one complete cycle. You can assume that. So Vm minus Vr, the drop in voltage will be nothing but the Vm minus Vr is the voltage just at the end of discharge cycle. This should be equal to, when we put t, small t equal to capital T over here, so this will come Vm 1 minus t by tau. We rearrange the terms a bit, so we get the formula for tau, that is the time constant, is t, which is the time period, times Vm, that is the maximum voltage, maximum input voltage, over Vr, that is the ripple voltage. Mind you, this is the ripple voltage that we have defined over here. So this was the formula that we obtained. Now I just put in the values. T is 20 milliseconds, as we denoted. We got this from frequency. This is 25 over 2. So this expression comes out to be 250 milliseconds. So time constant for this circuit is 250 milliseconds, and time constant nothing but RC. We know the value of C already, 500 microfarad. You put this and you get the value of R as 500 ohms, which happens to be option C. Okay. Now remember that we had assumed that this for only when time is less than tau, only then we can linearize it. So let's just check that whether this time the time constant that we have obtained is indeed much greater than the time period of the sinusoidal wave. So you can see that t, this is 20 milliseconds, right? Time period was 20 milliseconds and time constant was 250 milliseconds. So just t is indeed less than tau, and hence the linearization of exponent is a correct assumption. So this means this thing we can do, which was the basis for solving this circuit, right? So that's how we did it. Now just to summarize again, we what we did in this problem was, at this junction we equated the two voltages. That is that the drop, that is the voltage at this junction which is given by Vm minus Vr, which should be equal to, if you put the value of small t equal to capital T in this expression, and solving that we just got the value, we knew everything, and so we obtained the value of tau, and from we calculate the value of the resistor, and finally we just confirmed our assumption that which is indeed correct. Now moving on to the next problem. So this says, for the conditions given in question 1, what is the average diode current? So remember that. So let's just go to the solution. So this is the circuit I've replicated again. Now note that in this charge, as we knew, that this is the discharging part where the diode is off, and this part is the charging period when the diode is conducting, right? So I am denoting it in green. So this sinusoidal part is when diode is conducting, and this straight line is when diode is not conducting, right? And this is how the diode current will look like. So you can see that, so diode is off, so the current is 0 through this. So ignore this period for now, right? So just for the sake of, let's focus only here, right? So during this part diode current is 0, but at this junction diode current will peak, right? Will rise sharply, and then it will gradually decrease, and here we know the diode will turn off. Why? Because now we have a negative half cycle, and diode will become now clearly reverse bias. Hence you can see from this junction onwards the diode current is 0, and again when we hit this junction where the discharge cycle stops and charging cycle starts, that's when diode starts conducting, and it is denoted by again the sharp peak over here, right? So this is the ID waveform with respect to time. X-axis is time again, just like here, right? So what we are noticing here, the key thing to notice is that this is a sharp rise and then this is a fall. This kind of a profile which we see in the diode current. Now you might ask, why is the sharpness only here and why not here? It can slowly rise and then drop. Now if you remember that, if you remember, the diode current was something of the expression Is e to the power VBE over VT. This was the expression for a diode current. I'm ignoring the -1 over here, so let's just forget about that. So you can see that the higher the voltage applied across the diode, the higher will be the current, right? So, or VBE rather than VBE, this is a diode, so we can say VD, right? Is e raised to the power, let me write it again. So diode current is nothing but ID equal to some constant Is exponent of Vd over Vt. Vd is the voltage across the diode. Now just look carefully. When at this junction, when the discharge cycle has just ended, this capacitor is most discharged, right? And this voltage, so the difference between them would be highest, because as soon as it starts charging, as soon as we enter the charging cycle, this voltage will continue to rise, right? And so this will continue to rise. So we expect that the current through diode might start to drop, but we'll have to evaluate that, right? We'll have to see that whether it indeed drops or not. But this is just for the feel. You can take a feel of that, right? That this is the expression that's going to dictate the current, and this will depend on the voltage across the diode, right? So if it's forward bias, what is the voltage that is applied? Now let's whatever intuitively which you talked out, let's talk this in numerical term, right? So we know that since diode is on only for certain time of the input signal, right? Only for this part diode is on. That is, which is numerically you can define it when V input is greater than Vm minus Vr on the rising side. That is, this is the inputs, right? When the V in is greater than Vm minus Vr, this voltage is nothing but Vm minus Vr. This is the maximum, and note that this was the ripple voltage. This is how we define the ripple voltage. This is nothing but Vr, this voltage, right? So this is by the way the symbol for average, the greater than and less than sign, is equal to, how do you find the average? We integrate the ID over the whole time period 0 to t over the time period dt. Now this comes out to be, if you go through the lectures of Professor Patel, you'll see this evaluates to be Vm by R, right? So average diode current comes out to be Vm by R, but I told you that intuitively you can see that this will peak over here, right? So we saw that ID is Vm by R. We put in the values. Vm is 25. R we obtained in question 1 is 500. So we obtain that ID comes out to be 50 milliamps, which happens to be option A. Now this is just we told that you can refer to the formula, but is there some intuitive way of seeing it? Yes, there is. So you can say that. Now how do we obtain just the way to see is that just you average diode current. To obtain that, you just look at the in one cycle what is the capacitor current, right? So how do we do that? Now we notice that at the end of each cycle, right, at the end of each cycle this remains the same, right? The output voltage comes out to be the same value, that is Vm, right? So what actually is happening, this means the capacitor at the end of each cycle stores the same amount of charge, right? So this implies that all the energy that is being provided to the resistor, right, over a steady state must be provided only through diode, right? So we can say that average energy provided or average current provided to the resistor should be equal to the average current flowing through the diode, because capacitor will take care of itself. This is a crude way of putting it, so that's why I'm saying it. Mathematically you have to figure it out, which you refer to the lecture and you will see that, but crudely we can say that. So average of ID will be nothing but average of IR, which is nothing but Vm over R, right? And which is always coming out to be 50 milliamps. Okay, right. Now let's go on to the third problem. Now this says for the conditions given in question, what is the peak diode current? Note, we had just talked about it, peak diode current. We saw that the diode current does not, turns on only for a fraction of the cycle, right? But we saw that it peaks at the left edge, right? We just saw that, and then it drops. So as we were discussing that the ID will peak at this junction over here, right? So we are required to find ID peak equal to 0, and as we saw that diode is conducting only in this region, diode on, let's say, right? And this is the discharging phase, so diode is off here, so off in this region, in this whole region. So this is the time, and let's say this time is T0, sometime T0, okay? And so we are required to find ID peak. So what I'll do, I'll write KCL at, let's name this node A, KCL at node A at time t equal to T0 plus. So just after T0, what's happening? We want to see that. So just after T0, the diode will start conducting. So I can see that ID, this is the incoming current, so this will be ID. There will be a current flowing through this, we'll call it IC, and this current will call IR. This will be IC plus IR, right? So what is the value of IC? Now we know the value of IC for a capacitor. We know that the current flowing through the capacitor is C dV, the voltage across the capacitor, which in this case is V out. So dV out over dt plus the current flowing through the resistor. We have assumed that we are ignoring the ripple voltage when we talk about the current flowing through the resistor, and I can then simply write it as Vm over R. Okay, so if I expand it a bit, so dV out, right? So now we have to be careful. So we know that this region, remember we are in the region T equal to T0 plus, so just after T0. So we are in this region. This means this is nothing but the sinusoidal wave, right? So I can write the value of V out will be nothing but the sinusoidal wave, which is d by dt Vm sin omega t plus Vm by R. That term will continue as it is. If you differentiate it, Vm is a constant, it comes out, so it will be Vm times C times omega cos omega t plus Vm by R. And what's the value of t? T is nothing but T0 plus. Now we know everything in this expression. Omega we can obtain. Omega is nothing but 2 pi f. So omega is known. It's just that this time at time t equal to, so if we are required to put the value of t as capital T0 plus, but we don't know what is the value of capital T0 plus. We can determine that. So note that at this T0 plus, it is what's the value of this voltage here? So we can say that we'll call it the step 2 at t equal to T0 minus, right? So we can say that V out is nothing but Vm minus Vr. This is the maximum voltage and this is the ripple, right? So what's the output voltage? Vm minus Vr, and at t equal to t naught plus, what's V out? V out is nothing but Vm sine omega t, because just after this point it behaves like a sinusoidal function copying the input function. So that's, it will be this expression, and these should be the same. You can see that it's continuous. It's not differential, but it's continuous. So I'll put these values here. So I will write that Vm sine omega t naught should be equal to Vm minus Vr. That's what I have gotten, right? So from this I'll assume omega t naught to be theta. So I'll sine theta equal to Vm minus Vr over Vm. So this is the expression that I have gotten. Now from, if I know sine theta, this is nothing but cos theta, because t equal to t naught, remember we have to put t equal to t naught in this expression. So if I find sine theta, which I can find through here, and I can simply evaluate cos theta. So let's see what is the value of sine theta. So Vm is nothing but 25, ripple voltage is 2, so 25 minus 2 over 25. So this is 23 by 25. Okay, so let's now evaluate. Now put this expression of sine theta in this. So I'll write this expression over here. So id peak, which is nothing but id at t equal to t naught plus, this is nothing but Vm c omega cos omega t naught plus Vm by r, and we know that omega t naught is nothing but theta, and we have already obtained that sine theta is 23 by 25. So this will give me cos theta equal to let me just get the calculator. So it will be cos theta will be square root of 1 minus sine square theta, right? So this will be 0.92 squared 1 minus and square root of that. This is coming out to be 0.39. So cos theta value is 0.39. So let's put it here. The value of Vm is 25. The value of C is 500 micro. The value of omega, I told you the value of omega is nothing but 2 pi f. And f is 50. So this is coming out to be 100 pi. So into 100 pi. And cos theta, this is theta, you see it here, this is coming out to be 0.39 plus Vm is 25, R we obtained as 500 ohms. So we know everything over here, so we just have to solve this. So this will come out to be 125 into 0.39 pi, this will be 10 to the power 4, 2 zeros and 2 zeros, upon 10 to the power into 10 to the power minus 6, so it will be 1 over 100. Plus, so this will be 25 by 500 can be written as 5 by 100. Okay, so now let's evaluate this expression. So this will come out to be 125 times 0.39 times pi. This is coming out to be 154 approximately by 100. This is coming out to be 1.54. and this will come out to be 0.05. This will come out to be 1.59 and the units will be amperes. 1.59, yeah, so the closest option is D, 1.6, and that will be our answer for this problem. I'll just repeat what we had done in this. So we know that we need to find the ID peak, and ID peak will be at this junction, right? Because this is where the diode will start conducting, and otherwise the capacitor, after this the capacitor will start getting charged. You can clearly see that ID is coming out to be Vm cos omega t, and when theta increases, like cos theta will decrease, so the peak you will achieve at this junction. And how do you find this point which you denoted as T naught here? Well, simply we know that this is continuous. So T equal to T naught minus is nothing but Vm minus Vr. Vm is the peak, Vr is the ripple voltage, and T naught plus is nothing but given, it follows the input signal which is sinusoidal. We evaluate that, if we find the value of T naught, or in this case omega T naught, which you denote as theta, and finally we put it in this expression, and this is the ID peak definition. ID peak will be at T equal to T naught plus, and I put in the values, and we obtained the expression as 1.6. We obtained the value as 1.6 amperes. So that was the problem over there. And for the last problem of this set, now we are required to find what is the maximum reverse voltage across the diode. So this is an interesting problem. Now we are required to find what is the reverse voltage. So why would it be reverse biased? I told you, in this region diode is off. Diode is off, and only this discharge circuit is on, the RC circuit, and only in this small part diode is on, right? So let's evaluate that what is the reverse voltage seen by diode. Okay, so what I'm going to do, so this is the V out that we have over here. Let's draw what is VD. Okay, or let's write the expression for VD. So if I apply, so this is what I'm denoting as VD, right? So I can write VD is nothing but V in minus V out, right? VD is equal to V in minus V out, right? So V in we know is Vm sine omega t, where omega is nothing but your 2 pi f, frequency is known, minus V out, we'll assume it to be a constant, in this case Vm. Note, this is the V out, and we ignore the ripple voltage for now. So now this is the diode voltage, right? And we need to find the peak reverse voltage, right? So what is the max, what is the minimum this voltage can go? So what is the minimum VD can go? This will be minimized when sine omega, this is a constant, this will minimize when sine omega t is minimized, right? So VD is, just give me a moment.
Sorry, sir.
That's okay. Okay, so I will write that maximum reverse voltage would be seen when VD is minimized. So whatever the minimum value for this expression, that will be the maximum reverse voltage. So if to minimize this means sine omega t should be minimized. And how we do that? Sine omega t is maximum minus 1, so I can write that VD min is nothing but Vm times minus 1 minus Vm. This will be nothing but minus 2 Vm, which is minus 50 volts. So the peak reverse voltage that the diode will see, this is minus 50. So since we are talking about reverse voltage, so we'll just write the magnitude, which is 50 volts over here. So yeah, that completes our the half wave rectifier problems. So if you have any doubt about this, you can ask. Otherwise, we'll move forward. We have some time to spend over this particular problem of half wave rectifier. Just to complete the discussion, just like we have a half wave rectifier, we also have full wave rectifier. So in that, so the circuit is slightly different. You can see refer to the lecture notes. But in that case, what happens is that, so I'll draw this here. So in that case, so output is also over here. There are a few other diodes that are there, but in that case, so it will look something like this, and it will charge and then discharge, charge and then discharge. So its form changes a bit, but the principle remains the same. The diode is on for a certain period of time, and for the rest of the time the capacitor discharges through the RC circuit, and hence you see this straight line. And again, we will assume that the time constant of the circuit is much larger than the time period of the input waveform. So that's that. Now we move forward to our next sets of problems, which concern the transistors. But before we start with the transistors, I'll come to something very basic, which is resistor. So resistor is nothing but the potential difference between two terminals, and the potential difference between the two terminals will determine the current flowing between them. So for instance, you assume that this is a tube, and so potential on the left is equal to the right, and there's water filled in this. Nothing will happen because the you can see the pressure difference, and you may express anyway, but since the potential is the same, the water flow there will be no water flowing, It's denoted like here. However, if there is such condition that the potential on the left is greater than potential to the right, and you create a potential difference, what will happen is that like this, because the potential at the left is greater, so this edge is lifted up, so the water will start flowing towards the right. Similarly, if potential on the left is less than potential on the right, this means right edge is lifted, the water will start flowing in this direction. So what the lesson to be learned here is that only these two terminals, the potential difference between these two terminals determines the direction of the current and the magnitude also, depending on if we know the resistance for this tube, right? Transistor is a different thing. Transistor, a third terminal will control the current flowing between two other terminals. So here we have these two terminals, the left and right, and this central terminal. So the central terminal is high enough. You can see the water level is just barely above this center, right? What will happen is that very small amount of current, very small amount of water will flow. However, if I somehow lower this barrier, right, note that the left and right remain the same, they are at the same potential. However, if I lower the middle barrier, larger amount of water can flow. On the other side, if I lift the barrier, note the left side water level is the same as the first case. If I lift the barrier, the water will never be able to cross the barrier and come on the other side. So here no water will flow. So this is what a transistor is. That means the third terminal, the middle terminal, is controlling the water flowing between the left and the right terminal. This is what a transistor is. Trans means trans plus resistor, which makes transistor. And what do you mean by junction? Junction we refer to as the PN junctions, which are just like your typical diodes. Bipolar term means the current flowing is due to both the electrons and holes, and this is what makes a bipolar junction transistor. So this is what it is, and it comes in two flavors, NPN and PNP BJT. In NPN BJT, electron is the majority charge carrier and hole is the minority, and it's the opposite for PNP. For our discussion, we'll be restricting ourselves to NPN. If you understand NPN, PNP is just you can just the values will change, then the signs of the voltage will change, the functionality, the principles remain the same. And this is a schematic for, this is the symbol for that, by the way. So how to identify NPN versus PNP? The current will be flowing out, you can see that, from base to emitter. This is how we identify an NPN. For PNP, the current will be flowing, the arrows should be from emitter to base. This is PNP, and so this is emitter, base and collector, the three terminals. And a good thing to note is that emitter is usually moderately wide, base is narrow because you want very few recombination, and collector is wide to collect as many electrons as possible. Doping emitter is high because you want a large number of electrons to pass through. Base is low dope because you don't want any recombination, and collector is moderately doped. This is again the working of a NPN BJT in forward active mode. We'll see in a minute what forward active mode means, but what's happening is there, since this junction is forward bias, this PN junction, so huge amount of electrons will be injected. Since base is narrow and low dope, so a large amount, very few will recombine, which you see over here, but a large amount will be collected over collected over here at this terminal, and they will cross because there's a large electric field due to the reverse biasing of collector bias junction, which happens to be in the case of the forward active, and this is being denoted here itself. So you can see a large amount of current, electrons are coming, very few will recombine. This is the diffusion happening over here, while the drift is happening over here in the base collector region. And this is the KCL, IC equal to IC plus IB. Beta is the current gain, IC over IB. Alpha is the injector efficiency, that is IC over IE. These three, I mean, at least beta is frequently used, but sometimes you can also be given alpha. Okay. And so the three regions, as I told you, there are two terminals, NPN, so as I told you in this slide, you can see there are NP and then PN. So this can be forward, this can be forward, reverse forward. So there are four combinations which are listed here, and this is the region that we are most interested in, the active region, that is, right? So in this plot, but you can see that the active region is when base collector is reverse and base emitter is forward, and we are talking about this region essentially. In this big region between the line B and line C, this is the active region. When both are reverse bias, that the BJT is in cutoff, which you can see in this orange region over here. And if both are forward, is in saturation. This is in this you can see straight lines. This is just like a resistor behavior, right? V equal to IR. Okay, and finally there is a reverse active mode, which is not shown here, but usually we don't operate in that. So usually either we operate in active or in saturation. but for all purposes for this session, we'll assume that all our devices are operating in active region unless otherwise specified. So there's something called a load line. If we come to that, I'll explain what does this mean. But just the takeaway from this slide is that you will just assume that our BJT is operating in forward active mode, that is base collector is reverse and base emitter is forward bias. And these are some key assumptions that you must take, because for active, B I told you is forward bias, so that's 0.7 volts, and for saturation, to enter into saturation, VCE has to be 0.2 volts. So you can see that to enter into this region, right, that this junction B is the meeting point between saturation and active, so there is some voltage. In this case it's given 0.7, but for our problem says that take it to be 0.2, so we'll assume this to be 0.2 volts. And for PNP BJT, I told you the polarity is reversed, so VBE becomes VEB and rest all remains the same. And there's also the term comes VT, which you'll see in the expressions. It is assumed to be 26 millivolts at room temperature. So by room temperature I mean temperature equal to 300 kelvins, and that will be 27 degrees Celsius. And we'll assume a large beta unless the question says otherwise, right? So based with this simple understanding of a BJT and these assumptions, I'll pause here for a bit if there are any doubts. If not, then we'll start solving the problems. But just as I told you, a takeaway, we will assume it to be in forward active mode, the BJT, and these are the assumptions that we'll take. So any doubts? If not, then we'll move forward. All right, let's go ahead now. So this first question says, question number 5, but first for BJT, it says that consider an NPN BJT. So we are required for an NPN BJT, and I'll just draw these symbols so that this gets ingrained. So this is N, this is P, this is N, this is the symbol, right? It's operating in active mode at room temperature, so everything is given. Let IC equal to 2.5 milliamps. So this is the IC. Now this is the collector. This is given as 2.5 milliamps for some value of VBE. So this is B, this is E, B and E. So there is some voltage here, VBE. Okay. So how are IC and VBE related? There is a complicated expression, but for the purpose of this session, you can just assume that IC is equal to I naught e to the power VBE over VT. When this expression is valid when in active mode. Okay, this is valid only when it's in active mode. This is the expression. This is very similar to a diode expression where it is ID equal to IS e to the power VD over VT. So because this is actually a forward, this is actually a PN junction, and hence this derives, there are other algebra but we are ignoring for that. So this is the expression that we'll take. So it says that when VBE is increased by delta VBE, right, we want current to increase to 4 milliamps. So what's given is that IC1 is 2.5 milliamps, and this is some corresponding to VBE1, right? And there is some, we want this system now IC2 we want to be 4 milliamps, and for some other VBE as VBE2, and we're required to find VBE2 minus VBE1. So this is what's known as delta VBE, right? So let's just push this, so I'll put this value over here. So it will be 2.5 equal to I naught e to the power VBE1 over VT. What is this VT that I've been talking about? Remember in the last slide we saw VT is 26 millivolts for room temperature. This is that. So this is expression 1, and for this again I'll write 4 equal to I naught e to the power VBE2 over VT. This is my expression 2. This is the expression 1 and this is expression 2. So if I divide them, then I naught will disappear. So what I'll do, I'll simply do 2 divided by 1. So we'll get 4 by 2.5 equal to e to the power VBE2 by VT over VBE1 over VT. So this will come out to be 2.5 by 4. This is coming out to be 1.6. So 1.6 equal to, now these are two exponential terms, so I can write it as VBE2 minus VBE1 over VT. I'll take natural log on both sides, so this will be VBE2 minus VBE1 over Vt equal to ln of 1.6. So I'll just see what natural log of 1.6 is. That is 0.47. So this is 0.47, and this implies that delta VBE will come out to be Vt times 0.47. So if you multiply it by 26 millivolts, that's coming out to be 12.22 millivolts. 12.22 is our option B over here. And that's how we did this problem. So that just to summarize how we did, this is the expression that dictates the current flowing through a BJT in active mode. And there are two cases given, one when IC equal to 2.5, second case when IC equal to 4, and naturally they will correspond to different VBE because we are not changing VT, we are not changing I0. So I wrote this two expressions and then we divided them to obtain the value of delta VBE, which is VBE2 minus VBE1, which comes out to be 12.2 millivolts. So B is our option here. A very similar problem to this is the next problem that we are seeing here. So in this case also, this is an NPN BJT that's given. So let me draw that NPN BJT first. I told you it should be from base to emitter. If arrow is coming out, it's an NPN BJT. This is the collector, this is the emitter, and this is the base. Alright, again room temperature. So if it's a room temperature, we can clearly write that Vt equal to 26 millivolts. If VBE is reduced by 0.02, okay, so VBE, what is this? This is what's VBE, right? What is the percentage reduction in collector current? Okay, so there is some value. So first there is case 1. Okay, so even before that, let's write the expression for the current expression for BJT. So as we saw previously, that current expression will be something like IC equal to I0 e to the power VBE over Vt. Okay, so now I'll write the first case. So case 1 is when I'll assume the current is IC and the voltage is VBE. Okay, just give me a sec. Okay, so what I'll do, so what will the expression in this case would be, let's call this IC1 and VBE1. Okay, so if I put these values here, I'll get IC1 equal to I0 e to the power VBE1 over Vt. We'll call this as expression 1. Case 2 would be when we'll say the current flowing is IC2. So this is the current that's flowing here, IC. So IC2, and correspondingly it says the VBE is reduced by 0.0 volts. So we'll write that VBE2, this is nothing but VBE1 minus 0.2. It's reduced by minus 0.02. Okay, I'll again put these values in this expression. So I'll get IC2 equal to I0 e to the power VBE2 by Vt. This is my expression 2. Again what I'll do, I'll divide 1 by 2. Okay, so I am dividing expression 1 by expression 2. So I'll get IC1 over IC2. I0 will get cancelled. It will be e to the power VBE1 over Vt divided by e to the power VBE2 over Vt. So this will give me IC1 over IC2. This should be equal to, so this is exponential, so it will become VBE1. We can subtract these terms, VBE2 over Vt. Now VBE1 minus VBE2, because is over here. VBE1 minus VBE2 is nothing but 0.02 volts. Okay, so I'll write this here. So this will give me IC1 over IC2 equal to e to the power 0.02, and this is 26 millivolts. I'll write this here, right? So now I'll evaluate this expression. So it's 0.02 divided by 0.026 volts, right? So this comes out to be 0.76, and if I write the exponential, this is coming out to be 2.16. This expression is coming out to be 2.16. So this will give me that IC1 is 2.16 times IC2. What we are required to find is the percentage reduction in collector current. This means we are required to find this, I can say, reduction equal to IC2 minus IC1 over IC1 times 100, right? That is what we are required to find. Just make this clear. Yeah, this is IC2. Yeah, so if I divide it by IC1, so it will come out to be IC2 by IC1 minus 1 times 100. So from here I can get IC2 by IC1, right? IC2 by IC1 can be 1 over 2.16. so this will come out to be 1 over 2.16. this comes out to be 0.46. So I'll put this value here, 0.46 minus 1 times 100. This comes out to be minus 54%. What does the minus sign denote? Minus sign denotes that IC2 is less than IC1, which we expected, hence we are calling it a reduction. So we'll drop this minus sign because we've already included this term reduction here. So the answer would be A, 54%. So just to summarize, what happened in this problem was, just like in the last case, what we did, we wrote the expression for the expression connecting the collector current to the base emitter voltage. Again, I'll emphasize that this expression is valid when we are in active mode. Okay, when we did that, we wrote the two cases and we divided it, we did some algebra, and we finally find out what is the percentage reduction, which is IC2 minus IC1 over IC1. It's coming out to be 54%, which is the case here. Now the key thing to note is that note that VBE decreased only by 0.02 volts. That's very small voltage, that's 20 millivolts, but the collector current reduced by approximately 50%. It got halved. So hence the control on VBE is very important. Okay, a small change in VBE can lead to huge changes in collector current, and that's why there's something called biasing that is very important. So we need to, and the reduction of noise. So all those things are very important when you're talking about BJT, the circuits in BJT, right? So that's the takeaway from question number 5 and question number 6. Right, so just now I introduced the concept of biasing, right? So what do we mean by biasing? By biasing, we mean we provide certain voltages to base terminal, to collector terminal, to emitter terminal. That's what we mean by biasing. What is the DC voltage that we are applying to these terminals? And this will eventually determine, as we saw, what is the value of VBE and whether the BJT is operating in active mode or saturation mode or cutoff mode. This will be determined by that. Okay, so for this problem, we'll start, and it says that in the circuit shown, assume that the BJT with beta equal to 120, so beta is given, is operating in active region. So that's good, it's operating in active region. Just to reiterate, active would mean base emitter is forward and base collector is reverse. So I'm just repeating the definition, but it's good because now we'll see that whether this is actually the case or not. The question asks, what value of RB will result in a collector current of 0.8 milliamperes? Okay, so this is the expression. Beta is 120, IC is 0.8 milliamps. We are required to find the value of RB. These are the three currents that I have drawn on your screen, and these are the correspondingly node voltages denoting the three terminals of the BJT. And if we are required to find RB, now please note that we have already assumed, since this is in active mode, VBE is 0.7 volts. That is a given, right? Okay, so what I'll do, and okay, so what we'll do is that, so we'll apply KVL. Okay, to this we'll apply KVL along the green line. KVL along green line. Let's do that. This is step 1, let's say. So what we'll do, we'll write 2 minus IB times RB minus this drop VBE VBE minus IE times RE should be equal to 0. That is the expression that we'll get. Okay, and there's one more thing. If you recall that beta was IC upon IB, right? So I can clearly write that IC is nothing but beta IB, and IE is nothing but beta plus 1 times IB, because IE is nothing but IC plus IB, so that's how plus 1 comes. So what I'll do, I'll write the expression for IE over here. So I'll just rearrange some terms. I'll take IB to on the left side, so I'll write IB RB plus IE RE equal to 2 minus 0.7. VB is 0.7. Now I'll put in the values of okay, so it's even simpler. So what we'll do first of all is like this. Just wait a second. Yeah, so IC is known, right? So let's call this expression 1. Okay, so for second case, I know I will find out IB. IB is nothing but IC upon beta. What's the value of IC? IC is given 0.8 milliamps upon 120. So this will come out to be 0.8 over 120 comes out to be 6.67 microamps. Similarly, IE, I'll assume IE to be approximately equal to IC. Well, IE actually will be IC plus IB, but you see this is 0.8 milliamps and this is 6.67 microamps. So I'll ignore this term and I'll simply write it approximately equal to 0.8 milliamps. So I know IB and IE. Now what I'll do, put IB and IE in expression 1, right, which is this expression over here. So let's do that. So we have IB RB. IB value is 6. I'll write the expression here first. IB RB plus IE RE equal to 1.3. IB is 6.67 micro. RB we don't know. IE we know as 0.8 milli. RE we know as 680 equal to 1.3. This will give me RB equal to 1.3 minus 0.8 milli times 680 divided by 6.67 micro. So let's do that. So that 0.8 times 680 will come out to be 0.54. So that's milli. So that this is coming out to be 0.3 minus 0.544 divided by 6.67 micro. So this is 1 second. So 1.3 minus 0.544 divided by 6.67. 6.67. This is coming out to be around. This is coming out to be 0.113. 0.113, and this is in micro. So this will be 113. Yeah, 113 kilo ohms. Yeah, it will come out to 113 kilo ohms, which is the option D that we have over here. So this is the very simple problem in which we were given the collector current, and we are given an active region, and we are required to find the value of this the resistor RB, which is connected to the base. How we did it? We just simply write the KVL across this green loop, and then we simply evaluated IB and IE and put in the values over here, and to get the expression of RB as 113 kilo ohms. So as I told you, we have assumed this is in active region, right? So active region VBE should be 0.7, which is what we assume, but let's see what is VCE, right? So we must check. We'll check what is this VC and what is VE. We'll check in a minute, right? So we'll do that in the last. So or let's do it here itself. So VCE you can write. VC will be 12 minus. So what I'll do is I'll see what is VCE. Okay, VCB, not VCE, because VCB should be reverse bias, right? So VBC should be reverse, right? So we need to find what is the value of VB first, and then we need to find the value of VC. So VB can be written as 2 minus IB RB. This is coming out to be 2 minus 113K into the value of it's 1.6.67 micro, right? So this will come out to be 113 times 6.67. This will come to 0.75. Okay, so this is coming out to be 1.25 volts. Let's calculate VC. VC will be nothing but 12 minus ICRC. 12 minus ICRC. This will come out to be 12 minus 0.8 milli times. We don't know the value of RC, so we'll see in the next problem. If we find the value of RC, we'll try to evaluate that, but let's just leave it here. Okay, now it says what is the value of RC, which we are required to find in the last problem. To obtain VC equal to 6 volts, so we need VCE, this is C, this is E, in 6 volts, right? VC is equal to 6 volts, and again we are given in active region, so again we'll assume VBE equal to 0.7 volts. This is we are operating with this. Okay, so what we'll do is that again we'll provide we'll label the currents IC, IB and IE, and also we'll label the node voltages VB, VC and VE. And so now this time what we'll do is we'll apply KVL along this line. So I'll write step 1 KVL along green line. So let's do that. So it will be 12 minus ICRC minus VCE. So this is the voltage drop that it will see, minus VCE minus IERE minus IERE. This should be equal to 0, right? So I'll put the current terms on one side. So it will be ICRC plus IERE. This will be equal to 12 minus VCE. Now what I'll do, I'll assume IE is approximately equal to IC because beta is very high. You see beta is 120. So this is a safe assumption then. So I'll then IC will be common. It will become RC plus RE equal to 12 minus VC is 6. So this will become 6, right? So now what we'll have is IC will come out to be from here we see RC plus RE equal to 6 over IC. Now RE is known, but this fellow is not known. Okay, IC, but we know the IC from previous problem was given to be 0.8 milliamps, so we'll directly use that, because note that previous it was also in this is the problem is an extension of that, so please note that. So we know the IC is 0.8, so I'll write IRC plus RE equal to 6 over 0.8 milliamps. So this will give me 6 over 0.8 would be 6 over 0.8, so 7.5. So this is going to be 7.5 K. Milli is in there, so it will come K. So RC plus RE 7.5 K. So I'll write this over here, that RC plus RE is 7.5 kilo ohms. RE 680, so RC will come out to be 7.5 K minus 680 ohms. So this is 7500 minus 680 ohms. So this will come out to be deduct 700, 6820 ohms. This means 6.82 kilo ohms. There an option? Yeah, there's an option B over here. So that will be our answer. Since when is the screen not visible?
Joined now only.
Sorry?
I joined now only, and from the time I joined, I couldn't see the screen.
Okay. Okay. Sorry about that. Okay, so what I'll do is I'll quickly go through the problems that I had discussed. So in problem 7, we were given beta is 120, and it said that it's in active region, and so we are required to find what is the value of RB if the collector current of 0.8 milliamperes was given. So this is the problem statement, that if beta is 120, IC is 0.8, we are required to find RB. So I label the currents and the voltages. The voltages are in purple. So what I'll do is I'll apply KVL along the green line, right, which is over here. So I'll write 2 minus IBRB, the drop here, minus VBE, the drop here, minus IERE equal to 0. That's the KVL. Now what I'll do, I'll take current terms on one side and the voltage terms on the other. So it will come out to be IBRB plus IERE equal to 2 minus 0.7. So that will be my first expression 1, right? So we know this is 1.3, we know RE, we are required to find RB, but we don't know IB and IE. We can find that. How? Because we know IC is given and we know IB is nothing but IC upon beta. So I put in the values, I'll get IB equal to 6.67, and since beta is large, I'll assume that IE is approximately equal to IC. Essentially, I'm ignoring IB for this expression. IE will approximately come out to be 0.8 milliamps. So now we know IB, we know IE. We put this in this expression, which I have done here. I'll rearrange the terms. This is just simple algebra, and we'll obtain RB is 113 kilo ohms. That is over here, right? And we'll just see, so that was the option D over here. Now for second part of this problem, now we are given VCE also, right? So this is an extension of this previous problem. So in this previous problem, beta was 120, RB we obtained as 113, VCE is 6 volts, and VB, as we know, the problem says it's in forward active mode, so VB will be 0.7, and we don't know RC. So what I'll do, I'll simply apply KVL along this vertical line this time from collector to emitter, and I'll write 12. So this is the current IC and this is the node voltage VC. So 12 minus IC RC minus VCE, the drop along VCE, minus IERE, the drop in this resistor, equal to 0. Again, current terms on one side and the constants on the other. VC is 6, I put it here. This will give me IC times RC plus RE equal to 6. Why I can write IE equal to IC? Because beta is very large. So I'm essentially ignoring the role of IB in this expression. So RC plus RE is 6 over IC. IC we know from the previous problem was 0.8 milliamps. So I obtain RC plus RE is 7.5K. So RC plus RE is 7.5K. Now I'll simply put 7.5K. RE is known as 680. So RC will simply come out to be 6.82 kilo ohms, right? And as I was talking previously, this is in active mode. So in active mode, base emitter is forward, which is given to us because this was 0.7. The second thing is base collector is reverse, right? So let's see if it is indeed reverse or not. So we'll find, by doing that, we'll find VB. So VB is nothing but 2 minus IB RB. This is VB. This is VE. This is VC, right? So 2 minus IB times RB. So this will come out to be, IB was 6.67 micro. We obtained the previous problem. RB is 113K, right? If you solve this, this will come out to be 1.25 volts. So this voltage is coming out to be 1.25 volts, okay? And then we know that then VE will simply come out to be VB minus 0.7 because there's a 0.7 drop here. So this will come out to be 0.55 volts, right? And VC will be, is nothing but 6 plus VE. Why? Because VCE was given as 6. So VC is 6 volts above VE. That's what I've written here. This is coming out to be 6.55 volts. So this is 6.55. This is 0.55. And VB is 1.25. Now let's obtain VB minus VC. So VB minus VC will be 1.25 minus 6.55. This will come out to be minus 5.3 volts, which is a negative voltage. This means VBC junction is reverse biased, and hence our assumption that this is in forward active mode is correct. So it's a good practice when even when you solve the problem, just identify that whether assumption is correct or not. Okay, and we saw that this is indeed correct. Everything is according to our assumptions. So that's that. Now, next question asks, with RC set to the value obtained in Q8, so we obtained RC as 6.8K, right? So now RC 6.8K, what is the smallest value of RB which will cause the BJT to enter into saturation? Now if you remember the curves earlier, right, we talked about that there is a this curve looks something like this. So this is active, this is IC, this is VCE, right? And this is what we called VCE saturation. So right now we are operating here, right? But for whatever reason, if we, in this case, if we reduce the value of RB, for instance, right, so what, or increase, we'll see what happens. This might fall over in this region. This region is called the saturation region, right? So we are required to find when does that happen. So essentially we are required to find this point, right? And we are given that this saturation point is 0.2 volts. We are given initially, we saw some of the assumptions, right, that this saturation happens at VCE equal to 0.2 volts. Okay, so beta is 120, RC 6.8K, and we are required to find what is the minimum value of RB to enter saturation. Okay, so and again we'll see that VBE, because that will again remain forward biased, is 0.7 volts. Sorry, so this is the currents, these are the currents that we'll play with, and these are the node voltages, right? So now what we are required to find that what is the minimum at which that device falls into saturation. Okay, so I'll do that. Device enters saturation. When will our device enter into saturation? This will enter into saturation when VCE becomes less than 0.2 volts, less than equal to 0.2 volts. This is the equality denotes the onset of the saturation. Okay, so when this condition is satisfied, then our device will enter into saturation. Okay, so what I'll do now is I'll now apply KVL along this line. Okay, so we'll keep this in mind, we'll use this information. So let's write KVL along green line. Okay, let's write that. So it will be 12 minus ICRC minus VCE minus IERE equal to 0. Again I'll assume IE approximately equal to IC, because beta is large over here, right? So what I'll get is IC RC plus RE equal to 12 minus VCE, right? So from here what we will get is that VCE.
So right, what you write is not visible.
Again, just hold on.
Now we can see.
It is visible now?
Yes.
Okay.
Yes, sir.
Okay, so VCE I can write as 12 minus IC times RC plus RE. Now we know RC, we know RE, but what we don't know is this term IC over here, right? So that's what we are going to determine now. Now how do we determine this term IC? So what we'll do is that now let me go to a different color. Let me pick red now. Okay, so what I'll do is that now onset will happen when VC less than equal to 0.2 volts. Okay, so what we'll do is let's put this value 0.2 over here at onset, right? So I can write 12 minus IC times RC plus RE should be less than equal to 0.2 volts. I'm using this information. So this will give me IC should be greater than equal to, I'm taking IC to the other side, 12 minus 0.2 divided by RC plus RE. The value of RC is 6.8 and the value of RE is 680. So this sum will come out to be 7.5K, which we saw in the last problem. So this means that IC should be greater than equal to, the value of IC that I obtain is 11.8 numerator divided by 7.5. This is coming out to be 1.57 milliamps. So the value of IC should be greater than 1.57 milliamps. Okay, so now we'll use this information to how so what we'll do now, we'll now apply KVL along this loop. This will be step 3, KVL in red loop. So we'll do that. We'll write 2 minus RBIB minus VBE minus IERE should be equal to 0. Okay, so we know IC, right? So effectively we know IB and IE also, right? So what I'll do, I'll just rearrange these terms over here. So I can write IBRB plus IERE. We saw this expression earlier also. This is 2 minus 0.7 because VBE is 0.7. This is 1.3. So this is the expression that I have obtained here. Now what is the value of IB? IB I can obtain, so I'll do this here. So IC we have obtained as 1.57 milliamps. So simply IB will be IC by beta. So this will come out to be 1.57 divided by 120. This is coming out to be 13.1 microamps, and again I'll assume that IE is approximately equal to IC, which is equal to 1.57 milliamps, and the expression that we were playing with was this. So I'll write this here: IB RB plus IE RE is equal to 1.3. Now so what I'll do now is I'll simply put the values here. So this will be 13.1 micro times RB plus IE is 1.57 milli times 680 equal to 1.3. all right, so now let's just evaluate these expressions. So 1.57 milli times 680, so this will coming out to be 1.07. so RB will come out to be 1.3 minus 1.07 divided by 13.1 micro. So this will come out to be 0.23 divided by 13.1 micro. So this will come out to be 0.23 divided by 13.1. Just a second. It's coming out to be around it's coming out to be 17.017 divided by this is 10 to the power minus 6. So this will come, this answer should be around 17K approximately. I have made some assumptions here. So option C. Option C is the correct one. Now you might ask, why did I drop this inequality sign? So you can incorporate this inequality sign, because if IC is greater than this, then IB should be greater than this, right? But we are required to find the limiting case. So if you see, if you put IB value is greater than this, then RB should be, the sign would be inverted, right? So hence there will be inequality will come here like this, because IB should be greater than, and this equality should be satisfied. If IB is larger than some threshold voltage, then RB should be less than, hence this value will come. Or just to if you want to bypass all this confusion, just assume there's an equality and we are operating at the onset of saturation, and that will give you the answer, because sometimes inequalities can be confusing, right? So but we obtained this as 17K, right? So now we are done with that set of problems. Now we'll quickly move on to the other set, which is again this now includes the diodes as well as the BJT. Now you'll see that this is a PNP BJT. Remember why? How should I say that? Because this current arrow is flowing inside to the vertical. So this is your emitter, this is your base, this is your collector. So I told you the analysis does not change much, except BE will become EB and so on, right? Excuse me. So let's read the problem. The circuit shown in figure behaves like a current source. What's a current source? Current source is making a constant current through a load resistor RL. This means it will always provide this load resistor RL a constant current. That's what we mean by a current source. That's what we mean by the voltage source. What's a voltage source? Voltage source will provide a constant voltage to a specific load. That's a voltage source, but here it's a current source. So usually current sources are implemented using BJTs, or if you have heard, using MOSFETs. So we're not talking about this, but BJT is used as a current source, which we are seeing in this problem. It says that it behaves like a current source as long as RL is less than or equal to RL max. So this means there's a limit on below which it will behave like a current source. If the diode voltage is taken to be 0.7 volts, what is the value of RE required to obtain IL equal to 1 milliamps? So we are required to find what is the value of IL, and IL is given as 1 milliamps and VD on is given as 0.7. We are required to find the value of RE. All right, so let's go ahead doing that. So note that these are the currents that we know. This is IE, IB, and this is IL, which is nothing but IC, you can say, right? And these are the node voltages. So note that emitter is here. In the previous problem, emitter was here. Okay, so yeah, so let's go ahead and try to solve this problem. So what I'll do first is is the very first thing that we'll do is we can clearly write that that VEB, remember this time is VEB, this is equal to 0.7 volts, and also I'll simply say that IE is approximately equal to IC. IC is nothing but IL. Why? Because I'm assuming high beta. So this will be equal to 1 milliamps. Okay, so I'm assuming this current to be 1 milliamps throughout. All right. So so if this current is flowing like this, and it says that VD on equal to 0.7 volts. So let's try to find the value of VB. VB can be written as 15 minus 3 times 0.7. How I'm writing that? There will be a drop of 0.7 here, drop of 0.7 here, and drop of 0.7 here. So 15 minus VB is 3 times 0.7, or you can write VB equal to 15 minus 3 times 0.7. This will come out to be 12.9 volts. So this voltage that we have obtained is 12.9 volts. Okay, now, and we know now VEB equal to 0.7 volts because this is in active mode. This is conducting, so providing some current, right? This is in active mode. So VEB is nothing but VE minus VB equal to 0.7. So this will give VE equal to VB plus 0.7. This means this comes out to be 13.6 volts. So this voltage, right, is coming out to be 13.6 volts. Now as a step 3, you apply Ohm's law across RE. So we can simply write 15 minus VE by IE equal to RE. That's the Ohm's law. I'll write this over here. RE is 15 minus VE over 1 milliamps. What's the value of V is 13.6, so 15 minus 13.6 over 1 milli, this will become out to be 1.4 kilo ohms, which is option B. So very straightforward problem. We did nothing but we first find out VB. How did we find VB? Because these diodes are conducting, and that will be the source actually for this. That will be one of the KCL. If we apply here, that will be one of the components of current. And we know since it's forward active mode, so VB 0.7, we obtained VE through this, and then Ohm's law across RE gave us RE equal to 1.4 kilo ohms. Right. So now we are required to find in the circuit of question 10 what is RL max. Now how do we find the RL max? We'll now invoke the similar principles that we have invoked in the previous question. So what we did there, just give me a second. Yeah, so this is the problem. We are required to find the RL max. Okay, RE is given to be now 1.4K. These are the currents just as before, and these are the voltages. Now RL max, so note that we are required that this should operate as a current source. Please remember that this to operate as a current source. In order to operate as current source, device must be in active mode, right? This means VCE should be greater than equal to VCE SAT, which is okay. So in this case, because we are talking about PNP transistors, so we cannot say VCE. As I told you, we just reverse the nomenclature. So VEC should be greater than equal to VEC saturation. If this is ensured, this means you are not entering the saturation. Okay, and if this condition is satisfied, we'll be fine, right? So now what we are going to do is that to utilize this information, we'll apply KVL along this line. This was 0.1, 0.2, KVL along green line. Let's do that. So it will be 15 minus IERE minus VEC minus ILRL. This should be equal to 0. Now note that IL is nothing but IC. This is IC, and this is also equal to IE, assuming beta is high, right? So if we write everything, and so what I'll get here from is IE RE plus RL is equal to 15 minus VEC. Again, see, I am just operating at equality, right? As I told you in the previous, if you have problems with inequality, just take the equality case, that will be boundary case. Okay, this will come out to be now 14.8. So because this value is 0.2 volts. All right. So now what we get from here, and IE is nothing but 1 milliamp. So we get RE plus RL is equal to 14.8 by 1 milli. This is coming out to be 14.8 K, right? So RE plus RL is 14.8 K, and the value of RE plus RL is equal to 14.8 K, and the value of RE is given as 1.4 K. So RL will come out to be 14.8 minus 1.4 will come out to be 13.4 kilo ohms, which is option A. So that's how we'll get this answer. Now, even if you take the inequality over here, so how will you solve this? We'll simply do it like this. We'll write that if I do it in the inequality, so I'll write this in a different format. I'll write VEC equal to 15 minus IE times RE plus RL. I'll get this, right? And what I'll do, this should be greater than equal to 0.02. So let's do it that way also. This will be 15 minus IE RE plus RL should be greater than equal to 0.2. Again, from this you will get IE times RE plus RL should be less than equal to 14.8. From this you will get RE plus RL less than equal to 14.8. Okay, just note that this is the same expression except the inequality has also come. That's what I was talking about. Put the value of RE, you will get RL equal to less than equal to 13.4 K. So that's why I said you can skip the inequality, just work on the boundary case and you will be fine. Okay. The next problem asks, what is the diode current in the circuit of question 10? Okay, so question 10 is the problem that we are discussing. So this was the problem, and so wait one second. Yeah, this was the problem, and these are the currents, and we are required to find what is the value of ID. Now note that we had already obtained the value of VB. So if we know IC, which is equal to 1 milliamps, right? And so beta is, again I'm assuming to be high, just please make sure. So it should be IE equal to IC equal to 1 milliamps since beta is high. Okay, so now we are required to find the value of ID. Now ID is the current flowing through here. So now first I'll do is I'll apply KCL at VB node. That means at this node. Okay, so what's the incoming current? So incoming current is nothing but ID, this current, plus IB should be equal to I, this outgoing current, right? So I'll get ID equal to I minus IB. Now what is the value of I? I is nothing but current flowing through this resistor, which is VB over 4.7K. That's it, plus IB. The value of VB, if I remember correctly, we had obtained some time back. VB was 12.9. So what I'll do is that this will write 12.9 over 4.7K plus IB. So let's calculate this value. So 12.9 over 4.7, this is coming out to be 2.75 milliamps plus IB. So this is the value of ID that we have obtained, right? Now we just need to find the value of IB. How do we find IB? We know IC, but we don't know, so you can say IB equal to IC upon beta. Now beta is high. So what do you mean by high? By high, even if I assume, let's say beta equal to 100, which is a high enough value, so this will give me IB equal to 0.01 milliamps, right? And this is 2.75 milliamps. So this IB can be neglected with respect to the first term. That's what I mean to say. This IB is negligible, so I can approximate it to be 2.75 milliamps. Okay, so the answer would be 12th as D. Again, how did I do it? I did simply, we already know the value of VB and we apply KCL at this node. So it will be ID, incoming current, second incoming current is IB, should be equal to I, the outgoing current. And this is the expression. I calculate the value of the I, this outflowing current is coming out to 2.75 milliamps. And what I did not know, IB. Now IB will be significantly lower than IC, which is 1 milliamps. So if so, and if even if I assume beta equal to 100, right, which is high enough, so I would have gotten IB equal to 0.01 milliamps. If I neglect it, then I can neglect this 0.01 in terms of 2.75, and hence we'll get the final answer to be 2.75 milliamps. The closest answer is D, 2.74 milliamps over here. Right, so that completes our that set of problem. uh, I'll pause for a minute here. If you have 1 second. Okay, so I'll pause for a minute here, and if you have any comments or questions, please feel free to ask. We have a decent amount of time. We have got around 26 minutes, and I have only 3 problems to go. So if you have any comments or doubts, please ask. All right, if nothing, then we'll resume. Just 1 second. Yeah, screen is visible. Screen is visible, right? Just confirm.
Yes, sir.
Okay, good. So now we'll move ahead to the final problem set. So in this case, so first of all, as I always say, just try to identify the BJT. So if the arrow is coming out of the vertical line, this means it's an NPN BJT. And this is your N, the collector, this is P, this is N. The arrow side is always emitter. So in the circuit shown in the figure, assume that BJT has a large beta. Again, this is given large beta. The value of IB required to obtain IC equal to 1.2 milliamps. So this is again a very straightforward problem which we have solved something like this earlier. So beta is large, IC is 1.2 milliamps. What is the value of VB? How do we do that? We first label all the currents, the 3 currents IC, IB and IE, and the corresponding voltage VC, VE, and VB is already marked in the problem itself. So if IC is given and we are required to find what is the value of VB. Okay, so what I'll do first of all is, so step 1, find VE. Again, please remember we are operating in active region, right? So this is an assumption that we are making again. So find VE. So let's find VE. How do we find VE? Ohm's law across RE, right? If I apply Ohm's law across RE, this will be VE minus 5. What I'm doing here is this voltage minus this voltage, right? Just give me a second. Yeah, V equal to IR IE times RE. Okay, so now what I'll do is, now I can write VE plus 5 equal to, what's the value of IE? IEs will be approximately equal to IC because we are given beta equal to large. So I can write IC times the value of RE is given. That's now, so I'll write VE equal to, the value of IC is 1.2 milli, the value of RE is 680 ohms minus 5. Bringing it to this side, use the calculator. So 1.2 milli times 680, this is coming out to be 816. Okay, so 816, sorry, this is in milli, right? So by 1000 come out to be 0.816 minus 5. If we do that, this expression come out to be minus 4.18 volts. So VE we have obtained as minus 4.18 volts. Now step 2, we know VBE equal to 0.7 volts. Why? Forward active mode. That's what we had talked about. So VBE, so I can write is VB minus VE equal to 0.7. So I'll put this value of VE in this. So we'll get VB minus VE equal to 0.7. So VB will be VE plus 0.7. This is minus 4.18 plus 0.7. So this will come out to be minus 3.48 volts, minus 3.48 volts, rounding it off, minus 3.5 volts, which is our option C over here. So what I have done, I'll summarize. So we were given this problem, large beta. A large beta, what will that will ensure is that IC is approximately equal to IE. So that's the effect of large beta. IE will approximately be equal to IC, right? And so first, since we required to find VB, we first found out VE by how? By using Ohm's law across this, right? V was minus 4.2 approximately. Then we knew, since this transistor is operating in forward active mode and it's an NP and BJT, so we wrote this expression VB equal to 0.7 volts, and then using this V to the other side, we got VB is minus 3.5 volts. So you'll see a difference from the previous problems. In the previous problems, if you recall, so this is this problem, right? In the previous problems, like for instance, yeah, this problem, we had a resistor here also, right? This time it's different. This time the base, we are directly providing, in this problem we are directly providing a voltage to the base. Here there's no resistor here, so these are different. And these, the way where to add resistors, that is a thing that's a critical part of any circuit design. So we are not interested in circuit design here, but I am just telling you that while we are solving these problems related to the biasing of a transistor, the values of, we are finding the values of these resistors. So sometimes we are finding RC, sometimes we are finding RL, the upper limit on RL, the lower limit on RB, and so on. But the value of you'll appreciate the value of these resistances even more when you understand that these are required so that the device operates in a particular mode. So in the previous problem we saw, we wanted to operate as a current source, right? This problem here, we wanted to obtain as a current source, and we are required to find something called RL max, then only it will operate as a current source. So it's not like the value of RE and RL can be arbitrarily chosen. There's usually, depending on the application that we want to use it for, right, there is a certain how should I put it, there's a certain range of these values that we want to use. Okay, so just keep this in mind when we are solving this problem. This is the ultimate goal. Okay, so that's about this problem. Yeah, so that's about this problem. We had obtained the value of VB, right? So the next question asks, in the circuit of question 13, okay, what value of VB is required to obtain IC equal to 5 milliamps? So now the problem has changed. Remember, here IC was 1.2 milliamps, okay, and now we want IC as 5 milliamps. Now if you recall what we had talked about in the very first problems related to BJT, I wrote something like this for active region, right? This is the expression that we had seen for active region for BJTs, right? So you can see, if we change the only term of important, this is at room temperature, this will be constant at 26 millivolts. I naught is dependent on how you fabricate this BJT, which will, for all practical purposes, it will remain constant for us. The only thing that we can play with is VB and VE, and to be more precise, their difference, right? So if you change their difference, what their values is, and also what is the value of VC, right, you can change whether the device is in active mode or saturation mode, right? We saw that it goes into saturation. We saw the onset of saturation, problems like that. So this VB is important in that aspect. Okay, now we want current to be increased to 5 milliamps, and we are required to find what is the value of VB here. So let's do that now. So again, beta is large. So what will be the implication of beta is large? We'll again assume IE is approximately equal to IC, because IB will be very small. And then this time IC is 5 milliamps, sorry. So this is the current IC that is flowing, and IE, as I told you, is approximately equal to IC. These are the node voltages that we want. Now how do we go about solving this problem? This is the same problem. The how should I say this, the flow to approach this problem, the approach to this problem, sorry, remains the same. So just like we did in the last question, we said step 1. What was the step 1? So step 1 was that find VE, the emitter voltage, that is voltage over here. How do we find it? I apply Ohm's law across. RE. Let's do that. So I'll write VE, the voltage here, minus the voltage here, which is minus 5. So that is V equal to IR. The current flowing is IE, and the value of resistance is RE. Okay, this will give me VE plus 5. IE is approximately equal to IC, which is 5 milliamps. So I'll write it as 5 milliamps times RE. RE is nothing but 680 ohms. Right. This will give me VE equal to, so 5 times 680, 680 times 5, this is 3.4 minus 5, 5 will come that side. So this will give me VE equal to minus 1.6 volts. So now we have obtained VE equal to minus 1.6 volts. This is considerably higher. Remember, in the last problem we had seen what's the value of VE. VE was minus 4.18, minus 4.2. Now we are seeing VE has increased to minus 1.6 because there's more current flowing, right? So there will be more voltage drop here, and hence VE will also rise. Now for step 2, just like we did in the last time, we'll say that VBE is nothing but 0.7 volts. Why is that? Because device is operating in active region. That's the assumption that we have been operating with, right? So I'll write VB minus VE equal to 0.7. This will give me VB equal to VE plus 0.7. So VB equal to VE plus 0.7, VB equal to VE plus 0.7, VE we obtained as minus 1.6 volts plus 0.7, this will come out to be minus 0.9 volts. VB we have obtained as minus 0.9 volts, which happens to be option A. So just to summarize again, this is the very same process flow that we have discussed in the last question. Nothing has changed except that the current has increased, so accordingly the voltages will also change, right? Now again, what I'll do is here is that since the voltages have risen, I must also make sure that this is indeed operating in active region, right? So how do we make sure? As I told you, active region has two assumptions. Base emitter is forward, right? Second is base collector is reverse. So let's find out whether base collector is still reverse or not. Okay, so for that we need VB, right? We have that. So let's also find VC now. How do you find VC? So you find VC by applying Ohm's law across this resistor, right? So I can write 5, this is VC, and this is the current IC that is flowing. So I can write 5 minus VC equal to IC times RC, right? So from this I'll get VC equal to 5 minus IC RC. This will give me 5 minus, the value of IC is 5 milliamps times 820 ohms. Okay, so 820 ohms minus 5.
Hello, sir.
Yeah.
IC's value. Okay, given value IC.
Yeah, IC is given to us. So yeah, in the previous problem it was different. I think it was 1 milliamp. So now we have increased the current, right? So I want to be certain that we are operating in active region. That's why I'm doing this. Is not required for this problem, but as I told you, it's a good practice. Whatever you have assumed in your problem, once you obtain your answers, right, you just verify that whether your assumption was correct or not. Okay, so that's what I'm doing here. So this was 5 minus, this comes out to be 4.1 volts. So this comes out to be 0.9 volts. Okay, so now I have obtained VC as 0.9 volts. So I'll write this here. VC is 0.9 volts. VB I obtained as minus 0.9 volts. So as I told you, VBC should be reverse bias. How do we check that? You find VB minus VC. VB is minus 0.9, VC is 0.9, this is coming out to be minus 1.8 volts. This is a negative voltage, which clearly means that base collector junction is still reverse bias, and base emitter we have assumed to be forward bias. So this means both of these assumptions are in sync with each other. They are compatible with each other. Hence our assumption that the BJT is in active region is indeed correct, right? So that's what I did here. While we are at it, let's do this exercise here also, because this is, as I emphasize, this is a good practice. So as I told you, for active, base emitter should be forward and base collector should be reverse, right? So this means we need to find the value of VC here, right? And this is the value IC. So I'll again write Ohm's law across this resistor. I can simply say 5 minus VC equal to IC times RC. This will give me VC equal to 5 minus IC RC. Okay, so 5 minus 1 milliamps times 820. This is 5 minus 0.82. This will come out to be 4.18 volts. So VC is coming out to be now 4.18 volts. And if I see, you can clearly see VB is less than VC, but numerically if you want to find out, so this is minus 3.5 minus 4.18, this is coming out to be minus 7.68 volts. So this is VBC is negative, so this means that this is also reverse bias, so we are good. So our assumption that this BJT for this problem is in forward active mode was indeed a correct assumption, so there was no flaw in that. So that's what we did over here, right? So this was the second set of problem in this, and we had solved this, right? Now this is I was actually going to come to, so the last problem for today, it says that for the question circuit given here, what is the maximum value of VB for which BJT operates in active mode? This means the question is saying we have to stay in active mode. And if you recall the diagram that I presented earlier, so it's something like this, right? So this is your VCE SAT, this is your 0.2 volts. On a y-axis you have IC, here you have VCE, and this is the active region, and this was your saturation region, right? So we want to operate in active region, right? Here in this region, here. How do we do that? This means VCE should be greater than equal to VCE SAT, which is this value. So this means VCE should be greater than equal to 0.2 volts. So this is the condition that we work with, and then we'll, based on this condition, we'll impose some restrictions on the value of VB. We'll see what kind of restrictions come, but this is the expression that we have to work with, right? So again, beta is large, VBX to operate in active, VB, maximum VB to operate in active mode. This means I can write, as we saw in previous slide, VCE should be greater than equal to 0.2 volts. All right, so now these are the currents and these are the corresponding voltages for them, right? So what I'll do, because we have to impose a restriction on VCE, so I'll apply KVL along the green line, right? So let's apply KVL along green line. So let's do that. So I'll start from here. It will be 5 minus ICRC minus VCE minus IERE plus 5 is equal to 0. Why plus 5? Because I mean, you can assume there's a battery over here, that's why this plus 5 comes. All right, so what we'll do is that we'll take VCE to one hand and all the other terms to the other side. So VCE should be equal to 10 minus ICRC minus IERE. So 10 minus, yeah, this is correct. Okay, so what is IC and IE? So again, since beta is large, it's given, so I'll again assume IE is approximately equal to IC. All right, so let's do that. So this will come, VCE should be equal to 10 minus IC times RC plus RE, and we know this whole expression should be greater than equal to 0.2 volts. That's the condition that we have to operate with, right? So let's do that now. So this will be 10 minus IC times RC is 820, RE is 680. This should be greater than equal to 0.2 volts. So if I rearrange it, this will be IC times this will be 1.5K, 680 plus 820 plus 680. This should be less than equal to 9.8 volts. You take it to the other side, that's all I have done. So this will give us IC should be less than equal to 9.8 by 1.5K. So this will give me IC should be less than equal to 9.8 over 1.5k. So let's just evaluate this expression. 9.8 over 1.5. This is coming out to be 6.5. So IC should be less than equal to 6.5 milliamps. Okay, very good. But we are required to find the restriction on VB, right? How do we do that? So now we come to step 2. What is step 2? Find VE. The way we have been doing it earlier, right? How do we do that? Ohm's law. Ohm's law across RE. So if I do that, it will be, no, this is VE, okay, and this is nothing but IE. So I will write VE minus minus 5 equal to IE times RE. This will give me VE equal to, you take it to the other side, this will be minus 5 plus, the value of IE is nothing but IC, because again beta is large, right, plus, okay, so there is a condition imposed on IC, right? IC is less than equal to 6.5. This means VE will also be less than 6.5 milli times 680. This will give me VE should be less than equal to, I'll use my calculator, times 680, that's milli, so that's 4.44 minus 5, this is coming out to be minus 0.56 volts. So VE is coming out to be less than 0.56 volts. Now finally VBE equal to 0.7 volts. Why? Because we are operating in the active region. So this will give me VB minus VE equal to 0.7. This means that if I do this, this will give me VB equal to 0.7 plus VE, and VE maximum value is this. This means VB, inequality sign will persist, 0.7 minus 0.56, so this will come out to be 0.14. So the correct answer that we have obtained for this problem is VB should be less than equal to 0.14 volts, which is the option D. I'll summarize once what we had done here. So let's go to the first slide. Yeah, here. So the problem says,
Can we ask doubt in this current assignment?
yeah, you can. I have been encouraging that. This assignment.
Okay, week 4, fourth question. I worked it out to be 3.63, but the correct answer is 3.7. Is it okay or?
Okay, so you're asking the assignment which is live. That.
Yeah.
Okay. So I cannot solve the problem, but I can answer this problem. So what were the options?
I don't have option to share the screen.
No. If you can open on your, if you can open on
I'll
your
tell the question.
Sorry.
Like the same circuit which you solved. That is the base is grounded for a transistor.
Base is grounded. Okay.
Yes, and the collector is connected to plus 5 volt through a resistance RC.
Okay.
And the emitter is connected to minus 5 volt through a resistance RE.
Okay.
Okay, and the question is, what is the maximum value of RC for which the BJT operates in the active region?
So this will follow the exact same.
Yes. Yes, but when I worked out, IE is given 1.5 milliampere.
Okay.
That is
so that's fine. Numerically, whatever, if you're getting 3.63, and if the problem arises when the options are very close. So this is general tip for every MCQ. So for instance, you see I'll just let me complete this. So if I'm not 0.14, right? So let me complete my argument. If I have some answer, all right. So for instance, I obtained the answer to be minus 3.48 here, right? Correct. So if I round it off, I get minus 3.5. So let's say even if I had obtained, let's say minus 3.4 here, let's say, right? 3.4 is not an option, minus 3.4. I'll still mark the closest option. Okay.
But 3.63, if we round off also, we'll get only 3.6.
I get it.
But they're given 3.73.
That's what I'm saying, that you have to see what is the closest option to that, That's what I'm
Okay.
arguing. And plus, if the beta is so the way the discrepancy comes in these problems is that some people include, when you say, because throughout I have assumed IE approximately equal to IC.
I see. I also have solved like that only.
But some people who solve, they actually add the IB term also. So that slight discrepancy comes due to that. Okay, so
Okay.
1% or 2% error, that's how it propagates. Now, I should not say error, I'll say the differences between the two results. So that's how it comes from. All right. So,
Okay.
so that's,
And
yeah.
fifth problem, that is with a Zener diode. And I got the correct answer, but I want to know whether the way I worked out is correct.
Okay, the problem is I don't have the assignment at hand. So what I'll do is okay, just 1 second. I'll share my email ID. Okay, you just email
Okay.
me that, or there's a discussion forum, whatever you prefer. Just either share on the forum itself, or you can email me. So
Okay.
okay, so I'll share my email ID here. Second. So this is the email ID. If you want to, you can email the problem here. Not the problem. The problem as well as the solution.
Problem as well as the solution which I worked out.
Yes,
Both
yes.
I will.
Yeah, and because for Zener diode, I had solved problems in last class, I remember. Okay, so so if you want the link that I have shared, this is my YouTube channel. So I have uploaded the solution, the approach that I took to solve the problems of voltage regulator. You can just see through that. So if you find it good enough, you can use it. But nevertheless, you can email me your solution and the problem.
Okay.
Okay. Yeah, so that's that, and we are on time. I'm finished with the problems that I had scheduled for today, but I'll stick around if you have any doubts regarding to this session or the previous sessions. So today we had talked about the half wave rectifier circuit and the problem regarding the biasing of BJT. As I told you, the biasing is the values of VB, VC, VE we provide, and the design of the circuit. The design of the circuit includes the VB, VC, VE, as well as the resistance values like the RB, RC, and RE. So that completes in the circuit, the design of the circuit. So that's what we had worked out today. If you have any doubts regarding this session, please feel free to ask. Regarding previous sessions, I'll try to help as much as I can. And if not, we'll close this session.
Okay, we don't have any doubts. It was clear enough.
Okay. Thank you very much for staying around. Thank you for your patience.
Thank you.
Yeah.
Thank you, sir.
Yeah, okay. Good night.
Thank you. Bye.